Okay, let's get started. In this lesson we will start to discover the stretch constraint. The whole point of stretch constraint is to keep the initial distance between particles. You've probably already noticed that the stretch constraint interface is very similar to the bend constraint, the only thing that the stretch constraint has few properties that are unique to it. For example, the compression stiffness or warp weft option. The generated stretch constraints are all added to this primitive group. Now let's isolate the stretch constraint and see how it looks. Connect the constraint stream to the blast node. Then select stretch and check delete none selected. Look, this is the geometry of the stretch constraint, or the so-called distance constraint. Each edge in the display geometry is turned into a distance constraint maintaining that edge length. If we remove this checkbox, then we will see the bend constraint, which has a more complex structure. Okay, let's move on. The stretch has two types, both available for the cloth type of configuration. The default is the distance along edges, but you can change to triangle stretch, which works a little differently. Instead of just springs along the edges, each triangle is turned into a constraint that keeps the triangle as rigid as possible by removing any stretching or skewing according to the specified stiffness. Later we will definitely consider an example where we will clearly see the difference between them. Both types of stretch can be created individually as separate constraints. See, this is the triangle stretch constraint in a separate form. And this is the distance constraint. Well, let's return the cloth configuration type and move on. Distance constraint is the most basic part of vellum, so almost all types of constraints contain it. Look at the properties of the hair constraint, same distance constraint with the same interface. Let's choose something else, for example pressure constraint. Again it's the same here. Now I will quickly show you two more constraints and move forward. Look, here it is. And finally, let's select pin to target. Again, we have a distance constraint. So, in general the basic concept of vellum is to control the distance between the particle and the angle between them. Well, now I propose to consider in detail all the properties of the distance constraint. Let's start with stiffness, which controls how strongly the constraint pulls particles back towards their initial rest state. See, by default the highest value is set for stiffness, which means that practically it should not stretch at all. Now let's pin one point so that it hangs from it and see how it looks. As you see, it hardly stretches, although there is a barely noticeable springiness. But this is because we have a minimum sub-step. Well, now let's decently reduce the stiffness and see again. Look, how much is it stretching now, become like rubber. It also will swing up and down for a long time, and to dampen this, let's increase the damping ratio. Similar to the bend damping ratio, it will be bleeding energy when evaluating the constraint. As you can see, the swing up and down didn't last long, the energy was quickly dampened. If you increase it a little more, then the swing up and down will stop much earlier. Here we go, as it happened now. Okay, now let's revert to default the damping ratio, then we will continue to reduce the stretch stiffness and see what happens. Look how extremely it started to stretch now. The stretch strength is barely enough to overcome the force of gravity. If we continue to reduce the stiffness further, then there will come a moment when the force of gravity exceeds the stretch resistance, and as a result, it begins to fall endlessly. As it is happening now, it is not even enough to keep adjacent points together. Okay, now let's see how geometry resolution affects stretching. First let's make a stretch stiffness as high as possible and see how it looks, then we will change the resolution and compare. So this is how it looks like now. It almost does not stretch. Now, let's increase the resolution and check again. Since the topology has changed, the point numbers have changed too, so we need to re-specify the pin point. You see, it has already started to stretch quite noticeably, which was facilitated by a higher resolution geometry. To make it obvious, I suggest increase the resolution even more and look again. We again need to re-specify the pin point. So, let's see what we get. Now it began to stretch just like rubber, although we set the maximum stretch stiffness. So, you should always consider that dense geometry requires a large number of iterations to fight against stretching. Well, now I suggest increasing the number of iterations and looking again. As you can see, the result has changed dramatically, although there is still a slight stretch, but as soon as we increase the substeps, it will go away completely. Since we are going to increase the substeps, we no longer need such a large number of iterations, so let's set it to 300, then add 5 substeps, and check the result. Take a look, now it does not stretch at all. Good, I propose to move forward. Let's revert to default the iteration number and substep. We don't need such settings anymore. We also don't need such a dense mesh for further work. Since the topology has changed, we need to re-specify the pin point. This time we will pin both top corner points. Let's also lower the stiffness value to let it stretch a little. Now I want to demonstrate to you several important attributes related to stretching, which in the future will often be useful to us for various manipulations and just for debugging. First, I want to show you the stretch distance, which shows color according to how far constraints are stretched. The red areas are the most stretched and the purple areas are the least stretched. Well, now I'm going to show you another attribute, the stretch ratio, which visualize the color according the ratio between original and current stretch. There is another important attribute that we will often use to break constraints in the future. This is the stretch stress, which visualizes the color according to the maximum stretching force applied by the constraints. So the last attribute related to stretching is the stretch plastic flow, which visualizes the color according to how much the stretch plastic flow has been triggered, but since we have not yet turned on the plasticity, it will not show us anything. We will use it when we deal with plasticity. Okay, now let's scale the stretch stiffness by using the custom point attribute. Copy the default name, then drop down the attribute noise node. Pass the name here, then change the attribute class to float. Click on this icon to visualize the noise and then change the noise type to 0-centered values. Let's also increase the amplitude, then start to tweak the element size. Good, let's tweak the offset too. We can also edit the noise by this ramp. The last thing I want to do is limit the minimum value so that we don't have a zero stretch stiffness. Okay, before we check what we've got, let's pin all the top points. So let's check the result. As you can see, the cloth already stretches non-uniformly. In the red areas it does not stretch at all, and in the purple areas it stretches as much as possible. Let's make a few changes to the noise settings and look again. I also want to adjust the ramp. And the last change will be an increase in the minimum limit. Now we already have a slightly different result. It became in general less stretch as the minimum value of the noise increased. Finally, reduce the minimum noise value and check again. The purple regions began to stretch more. Okay, now let's visualize the stretch amount in different ways and see how they look. Let's start with stretch distance. Look, as soon as stretched, immediately becomes a red. Let's also check the stretch ratio. I will adjust the maximum value slightly. Pretty similar result. Finally, let's check the stretch stress and move on. This already looks more interesting. Now we can see where the constraints applies the maximum force. Okay, let's go on. The next thing I want to talk about is the rest length scale. For this I have provided another example file, so let's switch there. First, let's take a look at an example. See, I just randomly picked a few border points and pinned them. That's all I did, everything else is default. Now let's talk about the rest length of the distance constraints. It is the original distance between the points. This scale can be used to increase or decrease this. Setting to 0, we'll try to collapse the points together. So now let's put 0.8 and see what happens. Look, now the distance between the points has decreased by 20%, causing the geometry to shrink, and as a result, there was tension. If we continue to further reducing scale, the distance between the points will decrease even more. You see, the tension has increased because pinned points do not allow it to freely shrink as needed. It turns out that the original distance between points has been reduced by 50%. Now let's increase the scale on the contrary and see what happens. Exactly the opposite we got, the distance between points has increased by 30%, therefore the geometry has expanded. Now I want to animate the rest length scale. Let's make a 1 here, then dive inside DOP network and create a vellum constraint properties node. Connect to the force output, then specify the stretch constraint. Enable the rest length scale, then temporarily disable the dynamic simulation and start animating this parameter. See, now we have such an animation, it will shrink and expand several times by a different amount. So now let's enable the simulation and check what we get. As we expected, the rest length increases and decreases during the simulation, which leads to shrinking or expanding. Okay, let's move on. We can already delete this node, we don't need it anymore. Now I want to show you how you can manipulate the initial rest length. First, let's isolate the constraint stream and look at the primitive attributes. See, the vellum constraint node creates the rest length, which is the primitive attribute. That is, we can take this and modify it as we like, using the full power of the SOP. Let's drop down the primitive VOP and start modifying this attribute. Connect to the first input and the output goes to the solver. Then we will specify the stretch constraint and dive into the VOP network. In here, let's drop down the bind node. Then drop down the bind export just to rewrite the rest length after we modify it. In order to import the rest length, we just need to enter the correct name. Then copy this and paste into the bind export. Then just rewrite the rest length. Now let's create some noise. Connect P to the noise position and change the noise type, as well as reduce the noise amplitude. So now we just have to add the noise to the existing rest length. That's it, let's check the result. As you can see, we have a distorted initial rest length. As a result, we got these wrinkles. Let's tweak the offset of the noise and check again. Now it is distorted a little differently. So this is a great way to add the wrinkles or break the uniformity and so on. Now we will get smaller wrinkles. There you go. Since we added noise to the initial rest length, we can always change the total length in the constraint properties. Reduce the noise amplitude and then get out from here and decrease a little the overall rest length. So, let's have a look. See, it was shrunk, but the noise is still there. Now on the contrary, I want to scale up the overall rest length. Since there is no more tension, the noise has become more pronounced. And the last thing I want to do is reduce the amplitude of the noise and see again. That's it, we got a nice crumpled cloth. Okay, that's all for this lesson. In the next lesson, we will continue to discover the rest parameters of the distance constraint. See you in the next lesson.